All right, let's start. So today we are going to learn about software complexity. And here is today's outline. So first we will have an overview of software complexity, and then we will learn different levels of software complexity. And first, talking about complexity, I think you may have, if you have learned some advanced algorithms, you may have encountered this concept. So for example, you may have learned about the complexity for different searching algorithms. And when you learn about complexity for searching algorithms, you have learned about the time complexity, you have learned about space complexity, and it is often denoted as O1, On, or On square, something like this. And n refers to the input size. And O1 means is constant. So, but this is different from what we will learn today. So, this is the complexity you have learned in some algorithm courses is computational complexity, and it's actually different from software complexity. And here is a quick comparison from the concepts or the definitions. So for computational complexity, it is actually a theoretical measurement that is used to describe the resources required for an algorithm to solve a problem. And it is often described as a function of the size of the input. So this is it's actually quite formal, and it's often very accurate. So this is computational complexity, and understanding computational complexity is actually essential for designing algorithms and determining their feasibility for larger inputs, because if we see there's an exponential, if it is an exponential function, then we may know that this algorithm may perform badly on large inputs. And if it is a constant, then this algorithm may work well on larger inputs. So this is computational complexity for algorithms. And for software, it actually refers to the complexity of the software structure, design, and implementation. And it is often used to consider how hard it is to understand, to modify, or to maintain the software. So this is pretty different. And computational complexity is often very rigorous, and it could be calculated with some mathematics formulas. But for software complexity, it is more subjective to the measure, to what do we want to measure here. And high software complexity often leads to increased risks of bugs, maintenance difficulty, and slower development cycles. And this is actually why we are interested in software complexity in a software testing course, because often it is most of the time software complexity could lead to increased risks of bugs. So that's why, and we are interested in bugs in this course. So that's why we learned this in this course. And that's all about the overview of software complexity. And today is all about different metrics for measuring software complexity. And first, let's learn some unit level metrics. And the first one we will encounter today is called cyclomatic complexity. And have you heard about this before? No? Okay. So the definition is, so cyclomatic complexity could be measured for any graphs. And let's consider a not strongly connected graph. So strongly connected graph means we can reach from every node to another node, and it means that in a strongly connected graph, if we have a control flow graph and it is strongly connected, it means that there's an edge from the exit to the start. But that is not the practical case for most control flow graphs. So let's not consider a strongly connected graph. Let's just consider the normal ones we have encountered before. So in a control flow graph G, the cyclomatic complexity denoted as Cc is given by Cc equals to E minus n plus 2p. So E here is the number of edges, and n is the number of nodes, and p is the number of connected components. So in some cases we could have because there are some concepts in the graph theory called multi-graph, and in multi-graph we have multiple sub-components which are connected, and between the different components, they are not connected. So each p is a component here, and usually for one single function, we only have one p. So every node is connected into one component. So we don't have multiple different components here. So this means that if only one connected component is here in this formula, what we can have is Cc, the cyclomatic complexity, equals to the number of edges minus the number of nodes plus 2. So we can see that the number of edges has a positive effect on the cyclomatic complexity, and the number of nodes has a negative effect on this cyclomatic complexity. And for unit level calculation, we often use this formula here. So we don't consider the cases where we have multiple sub-components in the graph. So this is what we have, and it's actually pretty simple, a pretty simple concept. And let's try to practice using this concept. So let's consider this program. So can you imagine how does the CFG look like? So what is the control flow graph here? It's like a tree, right? It's like a tree here. And remember what we have just learned. The cyclomatic complexity equals to the number of edges minus the number of nodes plus 2. So what is the cyclomatic complexity here? One, yeah. 4 minus 5 plus 2 equals to 1. So this is a very simple example here. Let's consider some other examples by modifying this control flow graph, and let's consider which factors could affect the control flow graph, the cyclomatic complexity. So so we have actually known that if we have more branches, it is likely that we could have a higher value of cyclomatic complexity, because branches, whenever we have a branch, we will have more edges than nodes, right? So whenever we have a branch, we will have at least two edges connected to one node. So branches could positively affect this cyclomatic complexity. And let's learn more about which factors could affect this complexity. And let's consider adding some kind of dummy node to the end of this graph. So do you think this will increase the cyclomatic complexity here? Does this increase? No. Yeah, actually no, because it is calculated as E minus n, right? We introduced one edge and we introduced one node, and the effect is no. So this is not affecting the cyclomatic complexity. And what about this? We replace this node with a goto here. So let's loop back to line 1. So that this increase the cyclomatic complexity. Yes, right. Because we are not increasing the number of nodes, but we are increasing the number of edges. So the answer is yes. So could you see what's increasing the cyclomatic complexity here? Branches and loops. Branches and loops. Because whenever we have branches, we will have more edges connected to multiple edges connected to one node. And whenever we have a loop, it's essentially doing the same thing here. So branches and loops are positively affecting cyclomatic complexity here. And let's consider another example here. Let's try to do this. So assume we have a program like this. This is the original program. And let's do this. We add 2 more nodes, 2 more returns here. So does the CC increase if we attach 2 more nodes like this? No, right? It's pretty straightforward. But let's change the program a little bit. So what if we do this? Are we increasing the cyclomatic complexity here? Yes. Yeah. This is pretty straightforward. So can you see what is affecting the CC here? What's different from this one to this one? Actually, we have less returns or exit points. So actually returns and exits are, so you can see the term changed here. In the previous slides, I used increasing, and now I use affecting, because the number of returns and exits are negatively affecting the cyclomatic complexity. And if you go to search cyclomatic complexity online, you may encounter some materials that ignores returns, which is not really correct. So branches, loops, and returns are all affecting cyclomatic complexities. So why do we care about these factors that affects cyclomatic complexity? It is because just now we used a very simple example, and in reality, constructing control flow graphs could be very time consuming. We don't really want to construct a control flow graph for a very complex program just to calculate the software complexity, and that is extremely time consuming. So can we somehow, because we know that which factors are affecting the cyclomatic complexity, so can we just use these factors to quickly calculate cyclomatic complexity here? And the answer is yes, and this is the formula. So the formula is 2 plus the number of ifs plus the number of loops plus the number of cases in the switch statement minus the number of returns or exits. So let's come back to this program here, to this example here. If we use the calculation based on the previous formula based on the CFG, this is what we have. We use the number of edges minus the number of nodes plus 2, and it gives us the answer of 1. And what if we use the new formula here? So what can we get? We have 2 ifs here, right? We have 3 returns. We don't have any loops or cases. So the calculation is 2 plus 2 minus 3, which will also give us 1. So this is how we can quickly calculate cyclomatic complexity without constructing control flow graphs. So that's why we are interested in those factors that are affecting the cyclomatic complexity. And let's try to exercise with a more complex example here. So let's try to calculate the cyclomatic complexity for this function here. Remember, the calculation is 2 plus the number of ifs, the number of loops, the number of cases, minus the number of returns. So let's do a live poll here. So you have encountered some corner cases here. So default, right? Default case of the switch. Should it be counted or not? Anyway, you can just make a guess. And let's see the results. Oh, we have some people watching the live stream maybe. But the correct answer is 6. The correct answer is 6. So default does not count here. So let's try to reason why later. But let's try to have a look at the details. The detailed answer here. So this is actually the control flow graph of this program, and the cyclomatic complexity is 6. So if we use the number of edges minus the number of nodes plus 2 is actually 6. So if we use this quick calculation here, so we only count cases, we don't count default. And let's quickly go through the calculation of this. So we have the number of ifs. So how many ifs do we have? We have 2 ifs here, right? And how many loops do we have? We have 1 loop. And how many cases do we have? We have 2 cases. We don't count default. And how many returns do we have? We have 1 return. And the calculation gives us 6. So why we don't count default here? So you can imagine for an extreme case where we have a switch statement with only 1 default case with no other cases. So imagine we have only 1 switch with 1 default inside the switch. And then we will get only 1 basic block out of this switch, right? So this switch doesn't give us any branch. So the reason of counting cases is actually exactly the same as why we need to count ifs. Because every if will give us 1 more edge than the number of nodes. And for default, for switch, if there's only 1 default inside the switch, then it's not branching at all. So that's why we don't count default here. So we only count the number of cases. So this is how we can calculate cyclomatic complexity here. And there are actually some limitations of cyclomatic complexity. And you just now we know that, okay, the advantage is actually quite obvious. It's easy to calculate, and it can reflect the number, the complexity of the structure of this program, like the number of decision points, like the loops or switch or if else. But there are some limitations for cyclomatic complexity because it is like an oversimplification of the program. And the reason is that some making statements are not equal because some of them may have compound conditions, and they often involve more complex calculations for those conditions. And we can easily tweak the program to affect its cyclomatic complexity. For example, in this very simple pseudocode, we can have this is to justify whether three numbers can form a triangle or not. So so in this example here, we can get this very simple control flow graph. Let's consider this and if as an independent node. So the cyclomatic complexity for this graph is pretty simple. It's just 2, and we can also implement the program like this. So we can dissect this compound condition into multiple nested ifs, and this is what we can get. These two programs are essentially the same. These two programs are essentially the same, but the control flow graph is getting much more complicated, and we will increase the cyclomatic complexity here. So, but these programs are essentially the same, although this one is a little bit has some more dummy code. So, but the cyclomatic complexity are calculated differently. So this indicates that the limitation of cyclomatic complexities. So the first one is it has limited scope. So it only measures the control flow graph or the control flow complexity, and it doesn't count the data or computational complexity because each different decision-making points or conditions should be treated differently, because some of them may involve more calculations and some doesn't. So it has a limited scope. And of course, we can see that it actually ignores code size. So the first one is more like a longer code with a larger code with more lines in the linear sequence, because in the if it has 2 lines of actual code, and in the second example here, each one of the if actually is only associated with only at most one line of code. So a large function with a very long linear sequence of program statements will have a very low value of cyclomatic complexity. But even if for a procedural or sequential program, if we write a huge number of lines of code, we could still have many errors when we write that code, even if it doesn't have any branches. So ignoring code size is not a good idea in some cases. So that's why we need more metrics, and that's why we have this house-type metrics. And it is actually you can tell from the name it's named after some person, and it is actually proposed in 1977. It's very old, but it is still widely used nowadays. And this is what is driving the design of these set of metrics. So Haustide proposed that computer programs could be viewed as a collection of tokens, and these tokens could be categorized as either operators or operands. And because, remember, it is proposed in 1977, and by that time they don't have many advanced programming languages. They still use some hard, like some assembly code. And for assembly code, it is essentially each statement could be viewed as operators and operands, right? And for higher or for some more advanced programming languages, we could still convert the statements into the forms of operators and operands. So the Haustide metrics, so it is a set of metrics, are based on the following quantities, which is derived from the source code of the program. So the first metric is lowercase n1, which is to count the number of distinct operators. And the second one is to count the number of distinct operands, denoted as lowercase n2. And then we have the total number of operators, denoted by uppercase n1. And we have the total number of operands, denoted by uppercase n2. And on the basis of these quantities, we can have the following rules or metrics. The first one is program length. It is to count. It is denoted as uppercase n, and it is simply to count the total number of operators plus operands. This is quite straightforward. And then we have program vocabulary. It is to count the unique or the distinct number of operators plus operands. And then we have the calculation of program volume. Program volume is calculated as the uppercase n, the program length, times log2 program vocabulary. So this is the program volume. And then we have the calculation of program difficulty, which is calculated as the number of distinct operators times the total number of operands divided by 2 times the number of distinct operands. So this is how we calculate program difficulty using Haustide's metrics. And we have the programming effort calculated as the program volume times program difficulty. And Haustide's metric should be program independent, because essentially if we convert everything into assembly code, we can guide everything. We can guide the program as operators and operands. But for some programming higher level programming languages, there are some language features we should consider. So for different programming languages, we may have different rules for counting the number of operands and operators. So because everything is determined by the number of operands and operators. So let's have a look at the rules for C programming language. So This slide contains a lot of content, but it is only for documentary purpose. You don't have to remember everything in this slide, but I will go through them one by one here to explain. So the first one is the identifier and function declaration are not considered here. So whenever we declare a function or whenever we declare a new variable, it is not considered for the complexity counting. And the variables and constants are counted as operands. This is easy to understand. And the global variables used in different modules of the same program are counted as multiple occurrences of the same variable. So we count it multiple times if it is used in different modules. And local variables used with the same name in different functions are counted as unique operands. So we also count them multiple times when we count the total number of operands. And function calls are considered as operators. And all looping statements and all control statements, like the while loop, for loop, if else, and switch, are considered as operators. So these decision-related statements are considered as operators. And this is how we count switch. So the switch and all the case statements are considered as operators. And there are some reserved keywords like return, like default, like continue break are also considered as operators here. And goTo is considered as an operator. And the label of goTo is considered as an operand. In the array access, so whenever we access an element of the array, so the array name and the index are considered as operands. And the index access symbol is considered as an operator. In structures, the structure name and member name are considered as operands, and this access action is considered as operator. And the last one is, in some cases, we may use hash directives in C, and those are related to how the compiler compiles the program. So they are ignored. They are ignored because they don't affect the actual compiled binary we get. So they are ignored. And let's have a quick look at this example here. So this example is to calculate the day of week given the number of month, day, month, and year. So denoted as M, Y, and D. So if we get M, Y, and D, we can get the day of week. So let's try to apply and calculate the metrics for the house types metrics here. So what we need to do is we need to first count the number of operators, right? So what are the unique operators we have? So let's try to count them. So the first one is if. The second one is smaller than. And the third one is plus equal, minus equals. And then this assignment is another unique operator. And this modular and divide And what else? Plus, times. Do we have more? Do we have more unique operators? Actually, no, right? So these are all the unique operators we have. We have 9 unique operators. And then we also need to count the number of occurrences for each of these operators. And this is to calculate the total number of operators. So this will give us 21. And remember all the definitions here. So so the lowercase means distinct, and uppercase means total, and 1 means operators, 2 means operands. So let's try to calculate the operands here. And so the first unique operand is M, right? The second one is 3, because we need to count variables and constants as operands. And the third one is 12. The first one is Y. Fifth one is 1. And then we have K, 100, J, day of week. This is a variable, so we need to count it as an operand. And D is the next unique one. And 1, we have already encountered 1 before, so we don't need to count it here again. And 26, 10, K, we have already counted K. And then 4, we have already counted J and 4, so we don't count them again. And we have 5, we have 7. So all of these are the unique operands here. And in total, we have 15 unique operands. And similarly, we need to count their occurrences in order to get the total number of operands. And this is what we have. We have 25 as the total number of operands. And then once we have this table, once we have counted everything, we can apply the formulas to calculate different metrics here. So the program length is the total number of operators plus the total number of operands, and the number is 46. So it's basically the total number of tokens here. So the program vocabulary is like the total number of distinct operators and operands. And what we have is 24. And the program volume is calculated as 210.68. And then we have 7.50 as the program difficulty. And then we have the programming effort calculated as 1,580. So this is how we calculate House-Tide's metrics. And there are some additional metrics proposed by House-Tide, and they are time required to program. It is calculated as the number of programming effort divided by 18 seconds. And I don't know why he used 18, but this is maybe he did some experiments, but this is what we got. And the number of expected or delivered bugs is calculated as V divided by 3,000, the program volume divided by 3,000, or this is the more recent calculation, and there are some other calculations like this. We can use a cube root of e to the power of 2 divided by 3,000. And as far as the actual bugs of the implementation is lower than this expected numbers of bugs, then the program is considered as quite acceptable. So the quality of the program is considered as good. So let's have a look at the example again with the two new metrics. So and you will understand why I put them as additional metrics. So the time required to program is calculated as E divided by 18 seconds. And in this case, we have 87.78 seconds. And you can consider this function here. It's quite impossible to write a function like this or a program like this in 80 seconds, right? So, this is, however, this is what is calculated based on the definition. And the number of delivered bugs is expected to be 0.07. So, which means that we shouldn't have any bug if we write a program like this. But if you have done some kind of lead code practice, you may notice that this program is not easy to implement, and it could be very buggy if you actually implement this. So these two metrics are often not the case in reality. So that's why I put them as additional metrics, and let's focus on using the rest of the metrics to measure the complexity of the programs here. So that's all about unit level complexity, and let's have maybe 15 minutes of break or 14 minutes of break, and I'll see you at 3 o'clock. Alright, let's continue our second half. So, just now we have covered unit level complexity metrics. So, we have learned about cyclomatic complexity. We have learned a set of metrics from the Haussteid's metrics. And let's continue to learn some integration level complexity measurements. And remember, when we learn different levels of complexity, we learn the concept of call graph. So we have learned it before. When we learn unit level of testing, we learn integration level of testing. And a call graph is some kind of control flow graph that represents the call relationships between different subroutines in a program. So the terms used here are quite accurate. So it's not just functions but subroutines, and because in some cases we may use different methods to invoke another subroutine in some programs, and each node in the graph is considered as a procedure, and each edge indicates that one procedure invokes or calls another one. So it is called a call graph. And since it is a graph here, we can use cyclomatic complexity to calculate the complexity here. So can you quickly count what is a number of cyclomatic complexity for this graph? So in this way, we don't have the option to do the quick calculation for call graphs. So we have to build the call graph and calculate using the first calculation formula here. We need to use the number of edges minus the number of nodes plus 2 times the number of independent components here, because for some call graphs there could be multiple components. So maybe a set of functions are calling each other, but they are not connected with the other set of functions. So we may have multiple sub-components here. So P, the value of P plays an important role here in the calculation. So this is a little bit different from how we do the calculation on unit level. And then we have a special set of complexity calculation rules, which is object-oriented complexity. And I believe you have learned about object-oriented programming. And there are some important concepts in object-oriented programming. And the most important building blocks of object-oriented programs are classes and methods. And the calculation of the complexity is related to methods and classes. And this is one of the most famous metrics for calculating object-oriented software complexity is called the CK matrix, and it's also named after some people's name, and it is firstly proposed in 1990s. It's much later than Haussteid's metric. And then there are actually 6 metrics here, and the name of the metrics are almost self-explanatory. So we can indicate what does a metric calculate based on its name. So, but let's have but some of them are not very straightforward, and let's explain them one by one. So the first one, weight methods per class, so or WMC. So it is calculated as the sum of complexities of each individual methods of a particular class. And we can use cyclomatic complexity here. We can also use Halstead's complexity metric here. So it is just the sum of all the complexities of individual complexities of each method of the class. So it's pretty straightforward. And DIT, depth of inheritance tree. So for object-oriented programs, we have the inheritance between different classes, and this is just to calculate the depth of this inheritance tree. And the recommended DIT should be smaller than or equal to 3. So this is the second one. And then another metric here is NOC, number of child classes. It's also quite straightforward. It's related to the inheritance tree. So basically just count how many child classes inherit this class, and that is this metric, and it's very straightforward. And then we have coupling between classes, and this is how we count the coupling between classes. So a couple of the number of classes that are coupled to a particular class. So we need to count this CBO for each individual class, and it is calculated as where one of the methods of one class calls the methods or access the variables of another class. So it's basically the calling or invoking relations between different classes. And this is the call is two-way, is a bidirection edge or connection, which means that if, let's say, a method in class A calls a method in class B, then it will add one CBO for both class A and class B. So this is how we count the coupling between classes. And we also have response for class, and this is calculated by adding the number of methods in the class, not including the inherited methods from the parent classes, plus the number of distinct method calls made by the method in the class. So the keyword here is distinct. So each method call is counted only once. If this method is called across different methods of the class, it's only counted as one distinct method call. And you can have a look at an example here, and it will lead you to some online materials which provides a very good example. But let's not explain too much of details here. So basically, response for class is related to the counting of number of methods and method calls. And the last metric here is called lack of cohesion on methods. So in the design of OOP, we want to have high level of cohesion and lower levels of coherence. So lower level of coupling. So we need to have higher cohesions across methods. And this is how we calculate it. The first step is to identify the methods and attributes of the class. So we should list all the attributes and methods of a particular class. And then we determine the relationships between these methods and attributes. So a method is considered to use that to be related to an attribute if the method uses that attribute. So after listing all the attributes and methods, we need to somehow get the usage of the attributes by the methods. And after that, we can evaluate pairs of methods. So we can see if every two methods share attributes or not, whether they access the same attributes or not. And then we can calculate the lack of cohesion of methods. So we can calculate the number of method pairs that doesn't share any attributes. And then we calculate the number of pairs that share at least one attribute. And the value is calculated by using the first number to minus the second one, which means that we use the number of, because we want to calculate lack of cohesion. So the higher the value is, the lower the cohesion is. So if we don't have, so if the method pairs, if a method pair doesn't have any shared attribute, it means that there is a lack of cohesion. So we use this number here to minus the second number here. So this will give us lack of cohesion. And if the number, because this may sometimes give us a negative number, and if the value is negative, then the lack of cohesion on methods is set to 0, which means that the methods are not sharing any attributes at all. Let's try to use this example to demonstrate how do we calculate the LCOM, and let's follow the steps of the definition here. So the first step is to calculate or to list all the attributes and methods. So what are the attributes for this class? It's pretty straightforward, right? A1, A2, and A3. And what are the methods here? Yeah, M1, M2, and M3, yes. And then we need to do the second step. We need to decide which method is using which attributes. So for M1, it actually uses A1 and A2. M2 uses A2 and A3. M3 only uses A3. And this is what we get. And after that, we should evaluate pairs of methods here. So for M1 and M2, do they share attributes? They share attributes of A2, right? And for M1 and M3, do they share attributes? No. And for M2 and M3, do they share attributes? Yes. So this is what we get. So M1, M2, they share A2, so it's cohesive. And M1 and M3, they don't share any attributes, so it's non-cohesive. And M2 and M3, they share one attribute, and it is cohesive. So then we can calculate LCOM in the last step. So we have one non-cohesive pairs and two cohesive pairs. So we use 1 minus 2. This gives us minus 1. And because it's smaller than 0, we use the value of 0 here. So, which means that this class doesn't have the problem of lack of cohesive of methods. So this is the example here. And if you search the concept of LCOM online, if you Google it, you may encounter a lot of materials, and maybe each one of them is using a different method to do the calculation. And we use this one because it is part of the CK matrix, and there are also other definitions around. And I found a very good summary here, which is something like a research paper made by some people in the United States, and they have collected a very comprehensive collection of LCOM calculation methods, and you can have a look at them if you are interested. And let's continue. So after we have covered integration level of complexity, let's try to have a look at system level of complexity. And for system level of complexity, it is almost the same as integration level of complexity, but we just do it at the system level. However, there are some interesting findings when we do the complexity calculation on system levels. And this actually relates to an interesting research problem or a research question. So, is software complexity really positively related to vulnerabilities or bugs? So, if the complexity matrix gives us a higher value, does it always mean there is no bug? There is more bugs. There are more bugs. A higher value means more bugs. Does it always work like this? We can't say no, but it's actually hard to tell if we look at the system level of complexity. And there's actually an empirical study in 2018, that is 6 years ago, and in this research paper, the authors investigated a lot of defect or vulnerability detection methods, and this is a table of the methods they have evaluated. And you can see from the table that they evaluated a lot of advanced methods, like they may use different software complexity metrics to predict whether a program has more bugs or not. And they use even some machine learning or deep learning techniques to evaluate whether a program is buggy or not. And surprisingly, they have made an interesting finding, and that is most of the prediction methods cannot outperform the metric of simply counting the size of the program, like the lines of code. So if a program has more lines of code, it is likely to be buggier. So a lot of these advanced algorithms cannot outperform this simple count of program size. So software complexity is one of these, but some of the complexity metrics we have learned just now are somehow related to code size, right? Like house type metrics. So this is somehow an interesting finding here, but But we still need to learn the complexity, because just now I mentioned some of the metrics are still related to code size, and it is easier for us, and it is useful for us to predict buggy code. And now after covering all these metrics and the discussion of complexity with bugs, let's come back to testing or fuzzing, which is the key topic of this course. So why do we learn this software complexity in this course? Because it can actually help us to identify valuable targets for testing in a large system. And actually there's a practical tool developed by one of the a student in New York University, and this is a screenshot of the usage of the tool. And as you can see here, it is actually usable on both binary and source code. And this screenshot is from a binary program. As you can see here, this is .so file. It is actually a shared object or a shared library in Linux. And you can see here the function. Some of the function signatures, they don't even have symbols. They are replaced by the offset of the function in the binary. And you can see this. It actually reports fuzzability score, which means that this function is more interesting for testing. So if we test this program, we are more likely to find bugs according to this tool. And here is how the fuzzability score is calculated. We can see that, of course, this it actually uses some heuristics to see whether it is friendly for testing or not, and it also includes some complexity metrics like the number of loops, like cyclomatic complexity, which is the most widely used measurement for complexity nowadays. So it also has some kind of coverage depth, which is related to the call graph. So it is actually using both the unit level of complexity and some kind of integration level of complexity here with this tool. And that's why we need to learn software complexity, because it is useful for testing if we are faced with a very large system. So we may have to, because we have limited budget most of the time, and we may have to limit our testing effort to the targets with higher complexity or higher are more testing friendly. So you can try out this tool. And actually, during the break, I was trying to set up an environment to show you, to demonstrate you how to use this tool. But it seems that there's some kind of dependency errors when I was trying to install the tool. And that's why we need a Docker. And that's why we, in your assignment tool, you will be provided with some Dockers, so you don't have to worry about setting up the environments. But you have to be familiar with the basic usage of Dockers in this sense. So it actually helps you to avoid many dependency or environment issues here. And unfortunately, I can't show you a live demo of how to use this tool here. But okay, and that's all for the content today. And let's have a quick review of what we have learned today. So today we started from the overview of software complexity, and it is actually different from what you have learned during when you studied algorithms. It's different from those computational complexity, because computational complexity is more like a function of the time consumption or space consumption with regard to the input size, and it is more like a mathematical calculation kind of thing. And for software complexity, it's more subjective to what do we want to measure here. And some of them measures the structural complexity, some of them measures the computational or code size related complexity. And for structural complexity, we learned the concept of cyclomatic complexity. And for cyclomatic complexity, it could be calculated for any graph actually, and the calculation is based on the formula of E minus n plus 2p. So E means the number of edges, n means the number of nodes, and p means the number of individual connected sub-components. And for unit level of cyclomatic complexity, the value of p is normally 1. So we can just have E minus n plus 2. And we have we studied what are the different factors that could affect the value of cyclomatic complexity, and we learned about a quick way of calculating this cyclomatic complexity for any single functions, and the formula to calculate this is 2 plus the number of ifs plus the number of loops plus the number of cases not the default case, and minus the number of returns or exits. So in this way, we can just go through all the statements of the program to quickly calculate the cyclomatic complexity. And there are actually many tools around, even some IDE plugins for you to calculate cyclomatic complexity. And it's pretty easy to implement one by yourself. And that's cyclomatic complexity. And there are some limitations of this cyclomatic complexity, because it only there are two major limitations. The first one is CC is more focused on control flow complexity, and it doesn't count other types of complexity, and it actually has a very serious drawback of ignoring the code size. And we also learned that code size actually is a good measurement that may even outperform some advanced machine learning or deep learning predictors for bugs. So code size is important, and we do have some metrics related to code size, and they are the set of metrics called Haustalt's metrics, and it is mainly dealing with operators and operands, and we have covered the rules of how to count the operators and operands. And also for Haustalt's metrics, we covered some major metrics to calculate the program length, the program vocabulary, program volume, program difficulty, and programming efforts. But during that time, Haustalt also provides some other metrics, like how to calculate the time to do the programming, like the expected numbers of bugs, but they are not so practically useful. So we just use the metrics for program volume or programming efforts when we use Haustalt's metrics. And after that, we move on to learn about the integration level of complexity. And what we have learned are how do we apply, because cyclomatic complexity could be applied to any graph, and we learned how to use it for for the call graph to do integration level of cyclomatic complexity, and then we also learned some metrics, the C and K metrics for object-oriented software, and there are 6 metrics there, and one of the the trickiest one is LCOM, low cohesion of methods. And we learned one of the calculation methods, and there are a lot more, and you can explore them if you are interested. And then we learned, we know about a tool called Fuzzable, which could be used to help us to identify targets based on the software complexity metrics and some other small metrics. And that's how we learn. That's all for today, and see you on Thursday. We will be releasing the marks for assignment 1 this week, and also the specifications for assignment 2 this week. Yeah, it will be made an individual assignment, because I found it hard to make it fair for across groups and individuals. So especially for groups, you must have some kind of peer evaluation. And if you are grouping with your friends, then you almost guaranteed to get the full mark for the peer evaluation, which is unfair for those who are doing it individually. So I decided to make it an individual assignment in the end.